welcome our second speaker, Luke Davis, who's a theoretical physicist and applied mathematician. Luke completed his MPhys at Swansea, where he received the T.M. Davidson Prize, then a DPhil in theoretical physics at UCL, and has had postdoc positions at the University of Toronto, the University of Luxembourg, and UCL. And you will soon be able to find him at the INI in Cambridge, and then following that in Edinburgh. So thank you very much for coming to talk to us today. Luke is speaking on, if you cannot measure it, you cannot control it. Active matter under thermodynamic control, and maybe fridges.
Some mention of fridges, please. Yeah, so thank you to the organisers for this great talk, great conference. So yeah, the previous speaker also was a very entertaining talk, gave a beautiful historical overview of Kelvin and Thomson's life. So on the left, so actually this portrait wasn't shown. This is a nice portrait of Lord Kelvin. And on the right, you did see this. This is Lala Rook. And I mentioned this green notebook. So actually, Kelvin was good friends with Hermann von Helmholtz. And Helmholtz used to write that Kelvin used to organize social gatherings on his yacht, and Kelvin would immediately retire away in the cabin and write in his green notebook. So today is sort of half and half. I'll give you, I'll warm you up with a bit of history of thermodynamics, and then I'll sort of really bring you into kind of future considerations of thermodynamics of living systems, of what physicists like to call active matter, and what that actually means. I'll tell you later on. Okay. So slow this works. Okay, so thermodynamics has a very rich history. Many great minds have taken part in the building of thermodynamics, and I think so. I mean, you can also go back to Joseph Black, the Newcomen engine, and so on. But I think theoretical thermodynamics really started with Sadi Carnot, and Sadi was actually born. So Nicolas Sadi Carnot was born in 1796. As people here like William Rankine, so was mentioned that he's kind of vortex theory of energy. Rankine was one of the main proponents of that. In the middle is one of the senior figures in the history of thermodynamics. It's Rudolf Clausius, of course. There's Émile Clapeyron, who basically did one of the great jobs of translating Carnot's original work, which actually William Thomson ended up reading, and then sort of sharing to the rest of the world. There's Lord Kelvin. So Kelvin here is almost like, this is where I sort of drew the line. Of course, what's missing here is people like Walter Nernst, who actually came up with the third law of thermodynamics, Maxwell, Boltzmann, all these people. But I think they're really at the start of what's called statistical mechanics. And really, Clausius was the guy who handed over the baton to Boltzmann, Maxwell, and even Planck. So on the bottom, there was actually, I think, a better portrait of Joule. This is one where he's really looking quite old here. So this is Joule. In the middle, there's Hermann von Helmholtz. Helmholtz was a good friend of Kelvin, actually, and one of the sort of propounders of the mechanical equivalent of heat, and so was Julius von Mayer, actually. So Kelvin was the last to be born of this group of founders in 1824. Of course, we're celebrating his 200th anniversary. But actually, what I think is quite pertinent, on the same year, so the same year William Thomson was born, Sadi actually released to the world his reflections. So this text really was the start of theoretical thermodynamics. So this is the reflections of the motive power of fire by Carnot. But sadly, it was sort of not widely read, wasn't widely disseminated. But here, all the sort of theoretical underpinnings of thermodynamics were in this text. And indeed, William Thomson was fascinated by Carnot. He really picked up his work and really it was thanks to the championing of Carnot by Émile Clapeyron. So actually when Thomson, so it was mentioned that Thomson was in France in the labs of Victor Raynaud, and actually Thomson really wanted to get his hand on an edition of Reflections. So he famously went to a French bookshop, and he was like, "Do you have Carnot? Do you have Carnot?" And the bookkeeper was like, "Well, we do have one Carnot," but it was actually his father's book, Sir Lazare Carnot's, who really inspired his way of thinking. So I'm a physicist, not a historian of science. I do appreciate and indulge in history of science, but I really like to get stuck into the physics as soon as possible. So the sort of the new thing that Carnot brought about in theoretical thermodynamics was something called the Carnot cycle. So on the left, I have a plot, a diagram. So on the y-axis is something called pressure, P. On the x-axis is the volume. So you might actually recognize there's some equation in the middle equation on my t-shirt, which is Boyle's law. So Robert Boyle's preceded thermodynamics. But these are the same sort of variables in Boyle's law. And you can see there's different colored letters, A, B, C, and D. So actually, these are just different stages of a piston. So if we start our cycle from A, so when the piston is lower down, and what I do is if I expand the piston up to B, so this line follows something called an isothermal line. So this is TA. And actually, isothermal lines on the PV diagram are just equilateral hyperbola. So this is a sketch, right? So the axes are really asymptotes. And the steeper lines, so going from B to C, is something called an adiabatic expansion. So adiabatic in normal parlance just means not exchanging heat with the environment. And it's steeper because actually there's a really nice text by Enrico Fermi on thermodynamics. It's very small, where I learned about this. So basically you have PV equals a constant, but for an adiabatic expansion, you have P times V to some power alpha, where alpha is greater than 1. And so that's why adiabatic lines are always steeper than isothermal lines. Okay, so we went from B to C, and then of course we have to go back down again. So this is so we're walking backwards on the x-axis, so our piston is coming back down again, the volume is shrinking, and this is an isothermal compression. And then there's another adiabatic compression going from D to A. And this is, just a cycle. This is a heat engine. So really thinking in terms of a cycle was Carnot's sort of brilliant idea. So what differentiates thermodynamics with the more modern statistical mechanics is the sort of, we want to not care about the details of our systems, about the materials, about the molecules, and so on. So in this sense, thermodynamics is by construction one of the most general theories we have in physics. Because at the time, no one really believed in molecules, actually. It wasn't really known what actually happens on the molecular scale. It wasn't later until Boltzmann propounded the molecular theory, and even then, people like Mach didn't believe in atoms. Actually, it really came about from Einstein's explanation of Brownian motion. So Robert Brown was a botanist who, looking at pollen, he saw this jittery motion, and Einstein explained it. And really, from then on, people started to believe in molecules. So I've just sort of here abstracted away the piston. So you have here the red thing, which is just a hot reservoir at some temperature TA. QA is just the heat dissipated. So heat flows into the engine, work is produced, so it's W just work, and heat then leaves at a colder reservoir at temperature TV. So Carnot was really, he believed in the caloric theory of heat. He really thought of heat, that he talks about the fall of heat. heat flows from a hot reservoir to a cold reservoir. So in the caloric theory, Carnot said, well, heat is conserved. Heat flows from the higher temperature to a lower temperature, and it is never lost. So I have heat going from this hot reservoir to the engine, and the same amount of heat goes out to the cold reservoir, and I can still perform work. Of course, to our modern eyes, if you've just learned thermodynamics in school or university, this is obviously wrong. There's something wrong, and this is from the conservation of energy, of course. But at the time, this wasn't trivial. This was really a contention. So on the right, we have something called the mechanical theory, that indeed I have some heat coming in from the hot reservoir, and then the heat that's actually leaving has to be Q minus W. But so this might seem, again, we take this for granted, but at the time it was something that Thomson actually wrestled with in his mind for a long time. I think he probably stuck with the caloric theory, or even the main essence of the caloric theory, maybe for too long. So as mentioned, actually, this Oxford meeting where Joule presented results on a mechanical equivalent of heat. So this was the British Association for Advancement of Science, where Thomson was, wide-eyed looking at Joule's results. So the number that really pops out from Joule's experiments is 778, foot-pounds per British thermal unit. So there's British thermal units there, which we know, okay, it's still in calories, but this is 4.18 kilogram meters per calorie. So this number took Joule, it was painstaking to get these numbers. So Joule had to, some of these experiments, with the water paddle, so he would literally spin a paddle and measure basically the heat exchange from that. It was some of the most accurate, precise experiments of the day. So Joule really, these numbers, if he was to, so Boltzmann has the entry formula on his grade, I think Joule might have this number, should have this number on his grade. So William Thomson, after seeing Joule, and we saw this quote where he said, well, many of the ideas of Joule are wrong, but some, this really impressed upon Thomson's mind. Okay, so it's a bit, dotted around, but there was sort of refrigerators was mentioned. So actually, this is a good diagram of one coupled to a heat engine. Okay, so let me break this down. So on the top, I have the hot reservoir. On the bottom is the cold reservoir. So if we go from the left, so heat leaves the hot reservoir and enters an engine M. So it's gray because M, let's say, it's a real engine. It's not reversible. So work is produced, this work is W, and then heat leaves the engine into a cold reservoir. So some of this work feeds into the work that enters a reverse engine, so W prime. And it's green because, let's say, it's reversible. So what does a reversible engine mean? It means that, so I showed you the cycle, it means that every tiny bit of the cycle, I can go backwards in time, and everything's fine. And it's basically one that's, you move your engine very, very slowly, okay? So every point of the cycle, you have something called thermal equilibrium. So this really is a refrigerator on the right-hand side because work is coming in, heat is extracted from, this is QB prime, and then heat leaves the system, and this heat is QA prime. So the efficiency of these engines is eta. So eta M is just the work over the heat input. How much work can I extract from the heat input? And the same goes for eta M prime. Well, you have to be quite subtle here, but because M prime is reversible, I can state the efficiency like this. If it wasn't, I have to play another game. So we can just suppose that the heat that enters the real engine, so the grey engine, equals the heat that is absorbed from the refrigerator. So what Carnot did was suppose that the efficiency of the real engine is greater than the reversible engine. Well, that would mean that this W minus W prime is greater than 0. And this is what's called a perpetual motion machine of the first kind. So why is it astonishing? And it's astonishingly wrong, of course, as we know. Because Carnot believed in the caloric theory, so QB is also equal to QB prime. So no heat is ever exchanged between the two reservoirs, but you can get non-zero, you can get positive work without losing any heat. Of course, this is possible. Okay, so now if we put our hats on, so this is what Thomson really was thinking. So Clausius also had these thoughts, but the way Thomson sort of phrased it was closer to Carnot's logic. So Thomson then said, well, we know that there's something going wrong with the caloric theory. So let's just say this QB is equal to QA minus W. So this is really the mechanical viewpoint. And again, let's suppose that E to M, so the efficiency of the real engine is greater than the efficiency of the reversible engine. Well, this then implies that Q prime B minus QB is actually equal to this W minus W prime is greater than 0. So what this means is basically slightly different. You're taking up heat from the cold reservoir and you're using it to fuel work. And you can do this endlessly. Of course, again, astonishingly impossible. And this is the perpetual motion machine of the second kind. And this was rolled out by Kelvin and Clausius. So these were sort of principles or sort of empirical facts or postulates that the founders of thermodynamics had in their mind. Yeah, so let's talk about energy. So it was mentioned that the actual term thermodynamics was coined by Kelvin, was coined by Thomson, and so was energy, actually. And it was known, so part of the caloric theory was that heat was a state function. So the state, so the volume, the temperature, so the lower T isn't time, it's just something called the empirical temperature. A temperature that depends on the nature of the substance. And Kelvin, in his famous work in 1851 on the dynamical theory of heat, postulated this state function, that actually the state, there's this energy E. So Kelvin later called it the intrinsic energy. Helmholtz actually called it the internal energy, which is what we know of it today, right? Internal energy. And Kelvin then stated, okay, well, this small changes in the internal energy is just equal to heat transformation. That's the right-hand side. It's just energy transformations across boundaries. So you have this J, so this is sort of an ode to Joule. So you have J times dQ plus dW. It's weird because normally we can write Q in the same units as W, but actually at the time of Thomson, you had to sort of convert heat to the same units of work. And Joule's constant was there. So this is reminiscent, but I mean, this is essentially the first law of thermodynamics. But it would be wrong to say that Kelvin came up with this first. So Clausius actually just beat him to it. So in 1850, Clausius, in the mechanical theory of heat, really wrote down the first law and also the second law. So Clausius wrote, instead of small e, he wrote U, which is again the same letter we use in modern thermodynamics. And he wrote this basically. So P dV is essentially the work done. So if I go back, if my phone lets me. So the area shaded here is literally the work done. So P times dV is work. But Clausius really wrote it in this form here of dq. So Clausius really, so this is a subtle point. So Kelvin, more than Clausius, really realized the importance of the energy state function. Clausius was, I think, physically, he interpreted U as sort of an appendage of heat transformation. So Clausius was really still thinking about heat and work. So Kelvin was, I think, one of the first to really appreciate and realize the importance of energy itself, not just heat and work. So another thing that Kelvin, but we know Kelvin 4 is the absolute temperature. So he has a unit named after him, which is, as a physicist, I think one of the greatest things to happen to. So of course, Joule had one. And how did the Kelvin temperature come about? Well, Carnot had this in his reflection. He had this function. He said that the maximum efficiency was really only a function of a temperature difference, two temperatures. This is, again, we take it for granted. This is not trivial at the time. And it's nice because it's not wedded to any viewpoint on the molecular theory. I mean, it's just on the difference in temperature. You could be made of, I don't know, polystyrene or water, it doesn't matter. So Carnot's function received a lot of attention, and it can be written like this. We know that the maximum efficiency is just a change in work over the heat. And if it can only be a function of two temperatures, if I consider a very infinitesimal bit of the cycle, so I start at some empirical temperature T, and I just go to a slightly higher one, T plus dt, then that's an infinitesimal one. The only way mathematically this can come about in efficiency is some function f of this empirical temperature times dt, which I'll say is equivalent to some change in some substance-independent temperature. So f of t is something called Carnot's function, and many people sort of had their hands on it. So Joule, Helmholtz, and Clausius wrote it down. So Joule actually wrote it down with no proof. Helmholtz wrote it down with some errors. Clausius wrote down a very consistent proof of this, and the agreed upon form was this basically. So 1 over the empirical temperature plus 1 over beta, and beta isn't what we think is. So in physics, if you write beta, it's normally inverse kBt, right? Capital T, it's a Boltzmann's constant T. No, beta is just an expansion coefficient. So all these temperatures had to be related to the expansion of an ideal gas. So this just accounts for that. Okay. So what Kelvin did was, he said, okay, well, let me just posit a form of this equation. So he said, okay, let's take the efficiency. I know it's just some change of heat over Q. So again, this is really a mechanical viewpoint. So work and heat are interchangeable. So Carnot would never write down this first line of equation. And this is equal to some change in substance-independent temperature. Now the ratio of these heats, let's just say is the exponential of TA minus TB, and this is just by integrating, right? If I integrate Q, I get logarithm, and then I can exponentiate both sides. So Kelvin really for the first time wrote down that this T, this absolute temperature, has to be 1 over Carnot's function. And it's like this. So the conclusion of Kelvin's sort of analysis was that the ratio of heats only depended on the ratio of temperature. So this was an important result of Kelvin. And from this, Kelvin wrote down the second law of thermodynamics. I mean, he was also beaten to the punch by Clausius, but independently and recognizing Clausius, he came up with this second law. And he did this by realizing that the equation in blue can be written in the form on the right-hand side. So really it's about transformation. So delta QA over TA. And I put this minus sign in brackets because you can think of Q now as algebraic. I mean, if you properly account for if I'm absorbing heat from the environment, I'm positive. If I'm expelling heat, I'm negative. I mean, you could also do the reverse as long as you're consistent. then all the sum of these ratios will be 0. And for a reversible cycle, you get this. So the sum of all the exchanges of Qi over Ti is 0. So you might recognize that this is what really defines entropy. But Kelvin never wrote down entropy. He never wrote down. Actually, Kelvin stopped here. And this really isn't the full form of the second law, because the full form of the second law is an inequality. And Clausius was the first to write that the sum of Qi and Ti is greater than or equal to 0. So Clausius recognized irreversibility. So yeah, so Kelvin, I mean, he really was in the sort of building of thermodynamics, and he had points that some of the founders actually missed. So there's the importance of intrinsic energy and so on. So this is Kelvin's original statement of the second law. So he said, it is impossible by means of inanimate material agency to derive mechanical effect from any portion of matter by calling it below the temperature of the coldest of the surrounding objects. So then what about animate matter, living systems? So Kelvin really didn't consider living systems. I think later on, he sort of, instead of inanimate, he talks about organized matter. It's sort of maturing of Kelvin's thinking, where he's thinking about free will and humans. But for Kelvin, he really didn't see life in this picture. It was mentioned actually this age of the universe is debates with Darwin. Apart from that, he didn't really think about life. I think for me, so how I learned about sort of how thermodynamics imposes on living systems was from Erwin Schrödinger on what is life. So this is a great text. I think this is one of but this is not the original covering, of course, it's one of the modern ones on Amazon. So this is a great sort of, I guess, popular science book. But of course, animate matter, living systems, they have to obey the laws of thermodynamics in some sense. But do we have to amend these laws? Do we have to be a bit more subtle? There's some subtleties there that we don't know about. Okay, so this is where I'm going into my research work. So I've put you in the past, and now you're being fast forward into the sort of the current research in active matter, in non-equilibrium thermodynamics. So I'll be talking about control as well. So in terms of all the building of thermodynamics, there was always an intention, right? Like you talk about heat engines, cycles, extracting work. There was always sort of an external hand, a knob. And you'll see this here as well. So how can we control active systems? Now, what do I mean by active systems? I think probably one of the most beautiful demonstration of an active system is the murmuration of starlings. So I don't know if you've had the pleasure of seeing them, but also hearing them. Actually, if you hear a murmuration of starlings, it's quite actually awe-inspiring. So what happens is if they move in this sort of weird collective, I mean, it's beautiful, these shapes. So we move as a collective without a leader. So this really is the key point. So without a leader, they can move as a collective. So this sort of phenomenon you won't find in passive systems. Now I'm sort of introducing some terminology. I've introduced active and passive. So passive, what I mean by passive is, like the chair, table, water in a kettle. But if you leave it, if you just let go, leave it, it will reach some kind of thermal equilibrium. So all those sorts of systems can be explained by equilibrium thermodynamics. But for an active system, I mean, you just let birds do their thing. They're going to exhibit these weird behaviors. So active systems are intrinsically out of equilibrium. Now, what I'm showing you is an experiment, actually. So this is artificial man-made system. So here is micro-sized balls, colloids, where on one side of them, they're sort of coated a chemical. So if I shine light on the chemical, it causes a chemical reaction. that gives the makes the particle go vroom, right? It makes the particle go. And you can see here, so if I play it again, so when the light is switched on, you can see that these particles accumulate, they cluster, and there's no attraction between the particles, there's no stickiness, they're just bumping heads. But the one thing they have when the light is on is they have persistence in some direction. And just with those ingredients, you can get something called phase separation. So in active matter, it's called motility-induced phase separation. And when the light is off, they resume sort of passivity. So they become passive again, and it's just Einstein, they obey the Einstein relation. Okay, so the importance of this is that these basic experiments you would never get from passive systems. So we're in a completely different realm of phenomenology here. Now the question is, how can I control and design these systems? So one kind of fundamental equation that I study is a stochastic differential equation. So on the left-hand side, this is the kind of velocity. So as mentioned, Kelvin wrote dx over dt. What is that? Well, it's velocity, it's speed. And the subscript is an I, so I care about each particle, right? The first term is minus the derivative of potential, so it's a conservative force. And I care about, so alpha, just think of alpha as many different knobs that I can control the interactions between particles. And the last two terms represent, so eta represents not efficiency, eta represents thermal agitation. So it's sort of a coarse grained, what I mean, it's an approximation of lots of particles hitting me in a bath. And mu is an approximation of an active drive. So physicists in active matter, we call this a self-propulsion. So if I sort of hide V, if V goes away, I'm completely in a passive thermal case. Okay? So V makes the thing go vroom, right? It activates the system. Okay, so many of you, maybe not physicists here, but I think the key physicists love simple models. Okay, and I think Kelvin loves simple models that work. I can treat birds as arrows. Why not? With some direction and some alignment. This is a famous model in active matter. It's called the Vic model, actually. And just by considering some alignment and some noise, they flock, just as birds do. So just with these simple ingredients. And just in complete analogy with the experiments I showed you before, if I just consider repulsive disks, so they're just disks that take up some size, they have some noise and some active propulsion, I can get this phase separation I showed you before. So simple models can describe active matter quite well, and this is sort of key for physicists to sort of ask more deeper questions about thermodynamics control. Okay, so just to give you an overview of controlling active matter, so there's, what's active? All living systems, I think, are active, right? Even bacteria. So bacteria, when you just leave them on the plate, they sort of demonstrate this active turbulence, is what people say. And so, okay, let me take a step back. So active systems, they demonstrate behaviors that are not seen in passive technology. So maybe we can build the new materials and devices based on active matter to perform new functions that we just couldn't do before. So this motivates why we should control active matter. So people like to control bacteria, so controlling sort of the vortices in swirls of bacteria. How can I transport active droplets? And so this is just a list of papers. So this is really something of growing interest right now. And you can see here, there's the piston, right? The piston of these colloids. So we're still thinking, I think Carnot's thinking about the cycle is still very relevant even here. Okay. So I have to do my job about explaining the words that were in the title. So what is optimal control? Well, I want to go from one point in the phase diagram. So a phase diagram, if you're not a physicist, so it's just something like this, where in the blue region, there's some physics A, some behaviors A, And in the orange region, there's some other physics B, right? This is a fake diagram, it's just a schematic, it's not real physics. But let's just say I want to go from some behavior in A to some behavior in B. Well, there's many ways I can walk on this 2D plane. But there might be one that's really uniquely optimal. This is a dashed line. And okay, what am I optimizing? Usually it's something of this form. So J is something called the cost function or objective function. And it normally has this boundary term E, which only depends on the endpoint. So starting, t equals 0 to the final time. And you have something at the end that depends on the details of the protocol. So to a physicist, this reminds me of an action. So an action is sort of a time integral of Lagrangian. And again, as physicists, when we want to minimize something, we want to find a supremum of an action. So really, we can bring our intuition from, I guess someone mentioned Lagrangian. I mean, Lagrangian mechanics, the calculus of variations here. Okay, so how much time do I have left?
Like 5 minutes, and then there'll be 5 minutes for questions.
5 minutes. Okay, so I'll skip some of the details and just show you, I guess, some of the results. So what we've done is we've considered sort of the heat dissipation on this level. So we assume some ignorance that we don't really know how the bacteria, how the cells are burning their energy. We just know that we see them have some self-proportion. We can write the heat like this. So this is one of the main slides, actually. So on the bottom, it's reminiscent of the first law of thermodynamics. So Q equals du, so change in internal energy, plus work. But I have this extra term J, which depends on the activity. So remember, V makes my system active. If I kill J, I have exactly the first law of thermodynamics. So the thing about active systems is that if I turn off anything, if I stop controlling their knobs and so on, I kill the internal energy and I don't do any work, there's going to still be heat dissipated to the reservoirs, and this is J. So bacteria will heat, if you put your hands on a jar of bacteria, it's going to get hot because bacteria is still dissipating heat. And if you take this into account, then I'm always going to have a growing heat dissipation to the reservoirs. So this naturally means that there's a sort of finite optimal protocol duration for active systems. So we basically, in this work, we targeted this TP star and we just unrolled the carpet, right, systematically. And I won't go too much into the details here, but how we do it systematically, and again, it's sort of the thinking that was done previously. You consider an infinitesimal small change to the system. So what we do is we use a small perturbation to the system, and then you can use something called response theory. So this basically, I just expand terms in the heat, and I get these sort of R functions, and these R's are just the response functions, okay? So I can massage, right? I can massage equations, and I get this nice form, which looks like Rj, and this is really what we try to optimize. And the nice thing is that we have nice equations, so we get something like Lagrangians. Okay, there's systematic ways to get responses. Let me skip over that. So one key relation actually in thermodynamics and statistical mechanics is something called the fluctuation dissipation relation. It basically relates response of a system to correlation functions. And actually what we do get is these response relations for non-equilibrium systems. And if you kill activity, we get the classical Kubo relation. So basically, we're on safe ground. So instead of just formulas, let me show you some nice. So if I wanted to, a key thing in physics is to look at simple problems. If I want to sort of control an active particle in a trap, so if you're experimentally minded, you can think of this trap as like an optical, like a laser trap. And I want to just tighten this trap. So I'm confining the particle. So what we found actually is that in this bottom left, we found that these protocols really depend on whether you're tightening the trap really fast or really slow. And you sort of get this foliage of these solutions. And this really marks a departure from passive control. So in passive control, they all collapse onto a single curve. Okay, so this is quite a general thing of control active systems that we've revealed. So that's probably a bit too specialized. Okay, some nice movies. So I mentioned this sort of phase separation of active disks. So, you know, controlling a many body system out of equilibrium is difficult, right? And it's still quite difficult. So I think in terms of these basic models, we were really on the cutting edge of controlling many body systems here. So what I can do is I can inflate, like balloons, I can inflate a particle size. So if I inflate a particle size, I'm basically changing how much volume the particles are taking off the box, okay? So I'm changing the packing fraction. So on the left, if I'm blowing up the particles, you can see they're getting bigger, and as time goes on, they start to clusterize. And on the right, I'm doing the reverse, I'm deflating the particles. And of course, I can consider a cycle of inflation, deflation, and I get a sort of a loop, which is something physicists call hysteresis loop. And actually, these jumps mark when I sort of clusterize and declusterize. Okay, I'm saying these words. But actually, these rapid jumps make it very difficult for physicists to control active systems. And it's still an open problem how to drive a system through a phase transition, right? But it's not, we haven't solved that. We ended up just controlling small control within separate phases. But how to control optimally through a jump is still an open problem. And this is basically showing that we can really find the minimum of the heat dissipation for a collective. Okay, so one thing I can say is that we can do this. We can apply this framework for discrete state systems. So what does that mean to a layman? It means that if you have a system that jumps between different energy states, so it doesn't smoothly walk across the energy landscape. And this framework quite nicely deals with discrete state systems. So this work was done with Carl Prosmans, who's now at the Niels Bohr Institute in Copenhagen, and Etienne Fodor in Luxembourg. So to conclude, we sort of, I guess, created a roadmap for controlling active systems in a thermodynamically, in a thermodynamic way. What we found is that unlike passive control, protocols in active control do not collapse onto a single master curve. We've extended our theory to discrete state systems. So the resulting protocols can be used. So our work is, it's no machine learning. So we try and get some semi-analytical results. So the resulting protocols can be used to feed into AI, either as a testing bed or as it could make the machine learning algorithms perform better. And of course, we still have our eye on, driving through phase transitions. And I think it's important, and I think Kelvin was also good at this, of putting caveats and limitations on one's ideas and work. So one key contention in the field is about actually defining what's known as the heat dissipation. So I showed you a relation that boils down to the first law of thermodynamics when I get rid of activity. But I mentioned that I have some ignorance about how the bacteria, the cells, consume energy. So the cells and bacteria are really heat engines. And it's still sort of ongoing work about how to properly account for all the degrees of freedom of these bacteria and cells. So this is a good thing. Yeah, I think I'll finish that.
Thank you for a very interesting talk. Does anyone have any questions?
Lovely talk. You mentioned the first and second laws of thermodynamics, and you mentioned Clausius quite a lot.
Yes.
I cannot resist quoting what I regard as the most famous two-sentence passage in the history of science. Die Energie der Welt ist konstant. Die Entropie der Welt strebt einem Maximum zu.
Exactly, the entropy tends towards a maximum in the universe.
The energy of the universe is constant,
Yes.
the entropy of the universe strives towards
A
a
maximum,
maximum.
exactly.
That level.
No, exactly, and I think so this is a nice point because Calvin himself, so I didn't mention this, it hasn't been mentioned yet, he's often quoted with this heat death of the universe, right? That sort of a sobering thing that basically if you fast forward everything is just going to be fuzzy and heat will dominate everywhere. Which is pretty much saying the same thing.
Yeah.
And actually it was a nice thing, it wasn't really at the time you can prove that the Clausius statement of the second law and Calvin's statement of the second law are equivalent, actually. And there are versions of the second law that are a bit different. So there was a guy called Constantine Theodori who re-established the second law on an axiomatic basis. And there's some really interesting sort of mathematical implications of that. So, and that statement of the second law isn't equivalent to Clausius because you need something else. You need actually a postulate about Carnot efficiency. So there's many statements about the second law, and I think they ultimately go to the same thing, that the entropy of the universe tends towards a maximum.
Thank you so much. It was really interesting. I was curious about your hysteresis cycle. I don't think I understand what parameter are you tuning, and so you're showing volume. How is that related to motility in space approach?
Okay. So yeah, I wasn't clear most of the time. So this is good point. So this V is not volume actually. V is, it depends. It's a term in the heat that depends on the activity. So V, just for time, I didn't go too much into that. So V is this thing. So what I do is I take the heat dissipation, I sort of expand each term around a small perturbation, and I must massage, and V comes out. And V is basically, it just depends on this J. Sorry, I have to go all the way back. Do I even mention it? So basically V is this J term. So it's just a term in the heat that depends on the activity, and the hysteresis, oh god, I have to go all the way back. And what I'm changing here, so I'm going at the speed of an iPhone here. On the bottom, I'm literally changing the particle size, so the inflation. Yeah, so I can pick any observable really, well not any, but it's sort of arbitrary. We just wanted to see one term in the heat that contained the activity, and basically that, okay, of course we're going to get some hysteresis because there's memory in the system. So in the paper, this plot is not shown in the paper, because I think during the research it's like, okay, well, there are some issues about going through a phase transition. I think accounting for this loop is something that we haven't done, and I think needs to be done. If that answers your question.
So you're saying that by changing the size of these particles, you can observe some change in the heat exchange?
Yes, exactly. Yeah, because if I inflate the particle, I change the packing fraction, and so I can cross the phase boundary between mix and homogeneous gas. So
I think we're gonna have to save questions for lunch. It's now lunchtime. But yes, and maybe if there are any questions online, we can pass them over to Luke as well. But yes, thank you very much for a fascinating talk. And yeah, let's thank Luke again.